of this talk. Sorry. So first, I'm going to discuss what are exactly standard sirens, gravitational wave standard sirens. Then a classification which is done, which is basically in bright and dark sirens. And then I will discuss a little bit about the two main pipelines that are used to obtain the constraints on the cosmological parameters by the LIGO-Virgo collaboration, which are GW Cosmo and Icaro GW. And then I will talk about, can you hear me? Sorry? Yes, okay, thank you. So I will talk about some upgrades on the GW Cosmo pipeline that we were involved in. And these upgrades were in preparation for the fourth observing run. Then I will move on, after I talk about this, about some other work in which we were involved, which was blinded mock data challenge for gravitational wave cosmology. I mean, we, the cosmology group of the University of Antioquia, which is involved inside or within the LBK collaboration. Then, finally, I will move to some summary and perspectives about all these things. Okay, so what are exactly gravitational wave standard sirens? Basically, when you detect a gravitational wave from a compact binary coalescence object, you can estimate the distance directly from the amplitude of the wave, of the waveform. So basically, in the quadruple approximation, you have this analytical expression for the two polarization modes of the gravitational wave. So you can see that both of them are inversely proportional to the distance to the source. So that allows you, using the gravitational wave amplitude, to obtain some estimation for the distance. So this is the first ingredient you need to do cosmology. And this is also true for other kind of proofs, like electromagnetic proofs. You need the distance, and you combine the distance information with the redshift information in order to do the Hubble diagram and then constrain cosmological parameters, basically. So that's the key idea to do cosmology with gravitational waves, and that's the reason why these gravitational waves from these compact binary objects are denoted as gravitational wave standard sirens as well. So the first idea, for example, came from Schutz in 1986. And in that paper, he proposed to combine the gravitational wave information with galaxy catalogs information in order to do this kind of cosmological analysis. But then, in 2017, the LIGO-Virgo collaboration detected this golden event, which is the bright siren, the only bright siren that has been detected so far. And this is very important because in this case, the detection of the electromagnetic counterparts, that's why this is called a bright siren, because you detect the gravitational waves and you also detect the electromagnetic waves. So as many of you probably know, using the electromagnetic information, you can determine what's the host galaxy of this merger event, and then using this information, you can get the redshift of the source as well. So you have the distance from the gravitational wave and the redshift from the electromagnetic observations, and this leads to an independent measurement of cosmological parameters, such as the Hubble constant. And what I mean by independent is that this is independent from other proofs, from the electromagnetic proofs that can be used to obtain parameters such as the Hubble constant. When you don't have an electromagnetic counterpart, then you need to do some other kind of analysis in order to constrain cosmological parameters. So in that case, when you don't detect the electromagnetic counterparts, we talk about dark sirens. I like to mention it like a general thing, like dark sirens include what is called spectral sirens and what is called dark sirens. It's particularly the case when you also include the galaxy catalog information. So that's some distinction that is made, but I like to use the term dark siren for both cases, because in both cases you don't have the electromagnetic counterpart, so you have a dark event. You don't see light or any other electromagnetic information coming from the source. So One of the methods it's used when you don't have the electromagnetic information is the spectral siren method, in which basically you use the information of the compact binary population to infer cosmological parameters. And the key idea here is that there is a relation between the source frame mass of the events. Like there are two masses for a binary system. So the two masses, the two source frame masses are related to the detector frame masses through the redshift of the source. So there is this relation. And then if you have a bunch of events, statistically significant number of events, then you can do cosmology using some assumed mass distribution for the source frame mass of the CVC population. So, for example, in a previous paper, they used this for population models. There is this truncated power law for the primary mass, the broken power law, the power law plus peak. So this is a power law plus a Gaussian peak here, and then there is this other model, which is the multi-peak, which is a power law with two Gaussian peaks. The other method, which is what is called in the paper dark siren method, is incorporating not only the spectral siren information of the CVC population, but also the galaxy catalog information. So this has more information involved, and you can get better constraints, and I will show you later. And the idea here is that you can get some information of the redshift of the source from galaxy catalogs using the sky localization or sky location of the gravitational wave event. So for single events, this method is less informative than the bright siren method, but if you, as I mentioned also for the spectral siren method, if you have a significant number of events, then this method can give you compatible constraints of the Hubble constant, for example. So in this case, I am showing here a catalog which is GLADE, which is a compilation of different galaxy surveys that was used previously to do this kind of dark siren analysis. So now that we have all the ingredients, like how we incorporate the redshift information and the distance information, we can do cosmology. For example, for the bright siren case, we have, as I mentioned before, the redshift coming from the electromagnetic identification of the galaxy, and then the distance from the gravitational wave, and you can combine all those two things to get a constraint on the Hubble constant that was published in 2017, and this is basically the posterior on this cosmological parameter from this bright siren event. So one of the important things, and this is shown in this plot as well, is that as probably many of you know, there is a tension in cosmology, which is known as the Hubble tension. Basically, there is a difference between the estimated value of the Hubble constant from supernova local data, low redshift data, which is this constraint here in this orange color. And then in this kind of green color is the Planck measurement of the Hubble constant, which is smaller than the one that is estimated by Schuss. So there is this, the two confidence regions don't overlap, so that's why we have this tension. And the gravitational wave standards bright siren didn't give us anything like to solve it. But in principle, if we combine, or if we have many detections like this in the future, the constraint on this parameter coming from gravitational waves may give us some light on this Hubble tension, and that's one of the main motivations that for why we want to do cosmology with gravitational waves. Like we have this independent measurement. Yes.
What is the Schulz collaboration again? I kind of missed it.
Okay, so the Schulz collaboration is based on supernova and Cepheids data. So this is low redshift. So basically, I think they use the Hubble Space Telescope to get this data, and then from that data they make the distance ladder in order to constrain to make the double diagram and then constrain the Hubble constant. Okay. Okay, now the two pipelines that are used by the LIGO-Virgo collaboration in order to constrain these cosmological parameters are GW Cosmo and Icaro GW. So these pipelines, at the beginning, they were implementing two different methods. GW Cosmo, for instance, was implementing the dark siren method, assuming a fixed population model, so they were not constraining astrophysical population parameters while doing this analysis. So they use a specific mass model in order to do this kind of analysis. And here is the result that was obtained for the LIGO Virgo Kagra collaboration paper in 2023, published in 2023. This was with O3 data, and combining this blue curve here is combining the dark siren method with the bright siren event. And the other pipeline is ICARO-GW that at the beginning was developed in order to implement the spectral siren method. So they didn't use catalog information in their analysis, but then both pipelines were upgraded. So I will talk about some of the things that we were involved in GW Cosmo. But also ICARO-GW was upgraded in order to also incorporate the galaxy catalog information. So in this case, they performed the analysis using this catalog information, fixing the CVC population model in order to compare what they get with previous results from GW Cosmo. So that's what's the idea here. And now the two pipelines can do a joint inference, Bayesian inference, of cosmological and population parameters. And by population, I mean the mass model and other things that I will show you in a few moments. So how does this work? How does GW Cosmo, for example, work? So basically, the idea, and also this is the idea of ICARO-GW, is to perform a hierarchical Bayesian inference or analysis. So basically, you take the posterior of samples of individual events. So for individual events, you get an estimation of the distance, but also an estimation of the detector frame masses and other event parameters for each individual event. So that's basically done by parameter estimation pipelines. And then once you have those posterior samples, you use those posterior samples to compute the likelihood and the posterior of cosmological and CVC population parameters given those data, given those population, those individual parameter samples. So here the numerator is showing how the posterior samples information enters into this analysis. So basically these are the posteriors of the individual parameters given the gravitational wave data, all these things here. And the thing here is that this individual gravitational wave likelihood, so as you hear, this is a product between all the individual events. So these are n-detected events. So you marginalize over the individual parameters of each individual event, and then multiply all these things to get the likelihood, the numerator of this likelihood. Then the denominator of the likelihood is a term which accounts for gravitational wave selection effects, because not all the gravitational waves that are produced by compact binary coalescence are detected by your detectors, because there is some limits due to the sensitive and the noise that you have in your detector. So you have some selection effects. So for example, if the event is very far away and the masses are very small, so you don't get a signal which is strong enough to be detected. So, but it's produced, so you need to account for the fact that you don't see it, right? So these are the selection effects. So this we also call it like a probability of detection. And this is in the denominator. Okay. So in the case when you want to include the galaxy catalog information, you need to consider or use the sky location of the gravitational wave signal. And then this is something that, and also the marginalization over the redshift, because this is also an individual parameter of each event. This marginalization over the redshift is done in different ways for bright and dark sirens. And For bright sirens, usually you just assume a Gaussian distribution for the redshift with some mean given by the data, electromagnetic data, and some width given by the error of this data. Usually that's the most simple way to do it, but in any case, here I'm going to focus on the dark siren method because this is like more involved. And so the idea in the dark siren case is to use the gravitational wave event sky location to look for potential host galaxies in the galaxy catalog that you're using within that event sky area. So to do that, you can do a pixelization over the sky, so that simplify the problem. So you only focus on the pixels which are inside the sky location of each gravitational wave event. And also, this is also important because the telescopes are flux limited, so galaxy catalogs are incomplete, and you need to take this into account, and this incompleteness is different across different regions of the sky. So the pixelization is helping you to take all those things into account in a straightforward, in a more straightforward way. So basically, that's why the posterior it can be expanded in this way. So taking basically into account that you can sum over all the pixels that are located inside the sky localization of your gravitational wave event. So this is the denominator, and this is the numerator that I was showing previously. But here, the redshift parameter, the individual redshift of each source, is shown explicitly in this expression here. Now, in these preparations or this upgrade for O4, GW Cosmo, that GW Cosmo was that was done for GW Cosmo, there were some analyses that were performed on O3 events in order to check that these upgrades were consistent with other kind of analyses using that were performing also joint estimation of cosmological and population parameters. So in that case, the selection of the events, the criteria was that the SNR of events should be greater than 11. So this led us to 42 BBHs, 2 NSBHs, these ones too, and the asymmetric mass binary GW190814, which was considered an SBH for this analysis here, and 2 BNSs. One is the GW170817, and this other BNS. And in this case, for this analysis, the galaxy catalog that was used is an upgraded version of GLADE, which is called GLADE Plus, that contains a larger number of galaxies. And in this case, the redshift information that was used was obtained using the K-band of the galaxy survey. And this is a compilation of different galaxy catalogs as is shown here, and this is map showing like the density of galaxies per square degrees in the sky. Yeah.
So I was going to leave this question for the end, but now it came up here. The fact that there are some spots in the sky with much more galaxies than the others is again just because there are particular experiments that just looked at those little squares, and you are taking that into account in the expression you showed previously.
Yeah. I think that all these surveys don't look at the sky in the same positions. Not all of them look at the sky, the whole sky. So they look at particular places. So that gives you some regions with more galaxies than others, and also you need to take into account that the Milky Way band obscures galaxy survey. So that's also another thing that you need to take into account.
Yeah, so I had a similar question related to also the galaxy sample that you're using here. So you mentioned that for each of these different samples, you match the same redshift range, if I assume, right? Or how do you know, for example, that, because I imagine that each of the different samples has different redshift coverage in depth. So it could be possible that one of them it covers one region redshift, the other one other ones. How do you know?
So
Do you have a match between the whole samples to cover a specific range in redshift?
When you talk about sample, you mean the gravitational wave events?
No, the galaxy sample, the galaxy catalog population that you're using to. Because in here, for example, this is a pixelized map, but each pixel could contain galaxies in different redshift range, right?
I mean, of course, the low redshift everybody has. The problem is that different catalogs, they stretch to different redshift.
Right, but so then the the analysis in here is for different samples at different redshifts?
So you tend to include as much as you can, but there are some thresholds that you impose, for example, in magnitude. So in apparent magnitude, there are some thresholds.
Yeah.
And this threshold is done in a pixel by pixel case.
Yes.
So this is the Glade Plus. So actually, the catalog is, there is some processing of this catalog to compute the redshift prior, previous to the gravitational wave analysis. So when you do that, you pixelate the sky. So here is not pixelated. Here is just the survey, the galaxy completely. And when you do that, when you choose some resolution of the pixels, then for each pixel, in this case, the threshold of the magnitude of the apparent magnitude was the median apparent magnitude for each pixel, and that's the main cut. But I think there is also a redshift cut to exclude high redshift galaxies, because they are not so much reliable.
So because I always get confused a little bit when you try to measure these kind of things with gravitational waves, because, or both of you, Ricardo, and can correct me, but people usually don't know what is the redshift range that you're trying to look for when you're trying to get the gravitational wave, right? You don't know where it's coming from.
Yeah, you don't know what's the redshift.
Right. So then the idea of this is that you will get the redshift information from the galaxy that is located within the same pixel of the gravitational wave.
Yes, and this involves the galaxies at different redshifts in the same sky patch of.
I see. So one gravitational wave that comes from certain pixel could also have a certain redshift range.
Yeah,
depending on the catalog.
For sure, there is a redshift range, because all the galaxies in that pixel or that sky position must have different redshifts. So the idea is that when you consider many events, not the true redshift will come out, but the true value of the Hubble constant will come out of the statistical analysis.
Right, I see.
You never know what's the redshift, because these are dark science. So
yeah, I see. Perfect.
Basically the issue.
Thank you.
Okay, now, as I was mentioning, this analysis requires to assume some population models of, about the distribution of compact binary coalescence. So there are two key ingredients here that you need to take into account. One is the merger rate evolution, which basically we assume that this merger rate evolution in redshift follows a similar distribution to the star formation rate, because we assume that the binary black holes or the black holes and also the neutron stars come from astrophysical processes. So the idea is that the star formation rates is a tracer of this merger rate evolution of binary black holes. So that's one of the key ingredients. And the other key ingredient is the population of the distribution of the masses. So in this case, we assume some specific parametric distributions for the mass, the primary and the secondary masses. And this is the part in which we were involved, basically implementing these mass models into GW Cosmo. And in this analysis that I will show next, the primary distribution here is the power law plus the Gaussian peak, which is this one here, for the primary mass. So the primary mass is the largest mass in the binary, and the secondary mass, which is the lower mass, is described by a truncated power law with this slope beta for binary black hole systems. And for NSBHs, the secondary mass distribution is assumed to be a uniform distribution. So basically, assume that the neutron stars has uniform distribution in masses within some specific range between 1 and 3. Okay. And when we have binary neutron stars systems, both the primary and the secondary masses are described by the same uniform distribution.
So just a quick question and really basic. So why would you expect that the mass distribution will have peaks, or you will have a secondary peak or breaks, or?
Okay, that's a very good and interesting question related to how these systems are formed. Yeah, and this is kind of something that's, I would say, not very well understood, but like you can have a hierarchical um, um, production of black holes. Like first you have a black hole formed from a star, and then when they merge with another black hole also from another star or from another process, then they form another black hole, and this gives you some, this could give some peaks in the distribution of the binary black holes in the universe. That's what
Right.
I guess would be one of the mechanisms, but there could be others. I think many people investigate this, but I'm not very familiar with that.
I see. Thank you.
Okay, so for the analysis that was done here with O3 events, these were the priors on the population parameters. The prior for each node was 20 to 140 kilometers per second per megaparsec, and here are the parameters for the power law plus peak model. So these are the minimum and maximum masses of the black holes, the power law index, the index of the power law component of the distribution, the location of the peak of the Gaussian peak, the width of the peak. This parameter tells you how much the distribution is a power law, how much is the Gaussian for the mass model. Then there is a smoothing parameter to smooth the distribution at the lower end of the mass spectrum. And then there is this parameter for the secondary mass, and then the minimum and maximum masses of the neutron stars. Here we have the parameter describing the merger rate. So gamma, kappa, and zeta p are some parameters describing this Maddow-like Dickinson distribution. And the local merger rate in this case is not relevant because this prior guarantees that the results are independent of this parameter. So that's the idea in this case. So here are the results with the spectral siren analysis. This is not including the galaxy information, but later I will show you how the galaxy catalog information was used. And these six population parameters are the Hubble constant, one of the merger rate evolution parameters, the location of the Gaussian peak, the minimum and maximum masses of the black holes, and the width of the Gaussian peak. So here we have the marginalized posteriors of each individual parameter, and these 2D contour plots showing what kind of behavior we have between these two combination of parameters.
Characterization of these 42 events, 20 degrees square, 50 degrees square, do you have a...
Okay, that's a very good question. I'm not sure exactly what's the sky localization, but I will show later a plot which shows the squared degree area of these and 4 events. Okay, and here is the marginalized posterior on the Hubble constant, using these events and also using the Glade plus galaxy catalog information, and also the bright siren with its counterpart. And the key difference between this plot and the one that I was showing you earlier here is that in this case, the population was fixed to certain specific case population. Like the parameters of the population were chosen to be some specific values. But in this other case, this is the result of a joint analysis. So we sample over the population parameters as well. And then after marginalizing over the population parameters, this is the kind of constraints that you get from O3 data. And here it also, this shows the 1 sigma regions for the Planck and Choose estimations of the Hubble constant. Okay, now I will move on to the results that came out recently. These are using also the recently released GWTC4 catalog information, gravitational wave catalog information. And in this paper, basically the mass models were a bit different. So as I mentioned before, we were involved in this mass models implementation into Diablo Cosmo, but after that, some other mass models were implemented, and these models were also implemented in ICAR-GW as well. So the results that are shown here involves both codes, Diablo Cosmo and ICAR-GW. Basically, they took the 50% of the samples from Diablo Cosmo and 50% of the samples from ICAR-GW, and then they combined them together. And the mass models that were used mainly in the paper were the Paulo plus peak model that I just mentioned earlier for the O3 analysis, but also this multi-peak model that I mentioned that was used also for the O3 cosmology paper of ABK. These two mass models, the joint distribution of the primary and secondary masses, the priors distribution, have this form. So the primary has this individual probability distribution, which is one of these. So basically what I'm showing here is this plot shows the primary for all the cases. There are some smoothing functions at the lower end of the distribution, so this is not cut here like abruptly. And the probability of the secondary mass is conditioned to the probability of is conditioned to the primary mass. So that's the way this is modeled in these cases, the joint probability is modeled in these cases. And for this other case, which is called the full pop distribution, in this distribution, you use the same distribution for the primary and the secondary masses. And there is also something called the pairing function. So basically, the idea is that these joint distributions have to be zero whenever the secondary mass is larger than the primary. So to account that when you are passing the posterior samples, in the posterior samples, always the secondary mass is assumed to be the smallest mass in the system. So you need to take into account this into the joint distribution of the primary and secondary mass for your analysis. And the other difference between these two, these two groups of distributions is that in this case, your distribution is only used for the black holes, this mass. So this is the population of the primary black holes in the compact binary object. So these distributions are used when you have a binary black hole or an NSBH system, where the black hole is the primary mass always. But in this case, this full pop distribution, as the name suggests, spans the whole range of the CBC population. So you include here together the black holes distribution with the neutron star distribution. So this allows you to perform analysis with all the events together jointly, while these ones only allow you to do it with the events that have black holes. Or for example, only binary black holes, because you also need to take into account the secondary. So if you have NSBHs and BBHs, the distribution for the secondary mass is different in those two cases. So you can't do the analysis all together with all the events at the same time. So that's the main difference between this population here and this other two. And as I will show later, this distribution here also give some more narrow constraints, but they all overlap within the confidence interval for H0. So well, I will move on. So what were the events that were considered in this paper? In this paper, they used 142 gravitational wave events from this catalog. This catalog has many more events. But the idea here is that in order to do this analysis, you impose some conditions. For example, in this case, the condition was that these events have false alarm rate below certain threshold value, which is 0.25 per year. And this is a cut or a threshold that is imposed to all the events from O1 to O4A. And out of these 142 events, 137 are believed to be binary black hole systems. And the remaining 5 are, some of them are neutron star black hole system, and other are binary neutron star system. And out of these 142 events, 76 are dark sirens observed during O4A. 45 are dark sirens from O3 that were used in previous analysis, for example, the one I showed you before, but excluding one event. And another 20 events, 20 dark sirens from O3 that were not included in previous analysis. And basically that's because in the previous analysis they were using a different criteria for the selection of the events. So in this case it's only this false alarm rate criteria, but in the other they put a threshold on the false alarm rate, but and also on the SNR threshold, on the signal to noise ratio. So basically, in this case, this allowed to have many more events than in previous cases. So that's why there are also new events coming from O3 in this analysis. And we have also the bright siren event included in this analysis. This plot here shows the cumulative distribution of the O1, O2, O3, and O4A events, and also the O4A events separately, as a function of the sky location, or not the sky location, but the 90% region of the sky area of each event. So as you can see here, the O4A events are like the localization of some O1, O2, O3 events is better than for O4A. And that's basically because during this observing run, Virgo was not so, like operating. So the sky localization was worse than in O3, because in O3 Virgo was active. So you need these 3 detectors to have better sky constraints for each individual event. So that's what this plot is showing here. And this other plot is an overlap between the magnitude threshold map. This is, yes.
So the 76 comes from
O4A.
Yeah, but then you
which
say
are the blue.
76 is also 45 plus 20 plus 1. That's
No. Sorry, maybe this was a bit not clear. But these 45 are the other ones. So 142 are this 76 plus this other.
okay.
Yeah, maybe I was not totally clear here. Sorry.
No, sorry. 142 is made out of 76 from O4A plus 45 from O3. That makes 121.
Plus another 20 from O3 that were not used in the previous analysis.
Okay.
Because the SNR cut was applied in that case. And these other bright sirens. So this sums the 142. Okay, and yeah, the O4A here, this plot shows that the O4A in general are not so well localized as some of the O3 events here. And this other plot here is showing the overlap between the 10 better sky, the 10 better localized events in O4A, which are listed here, and the sky maps of those events. And in the background is the sky map of the magnitude threshold of the Glade Plus catalog, pixelated using a resolution of 64, side equal to 64. I think the area of each pixel is around 3.35 square degrees. Yes.
Sorry, I don't know if you mentioned before, but why did you change the criteria of the SNR cut to the false alarm rate this time?
Okay, Right now, I'm not totally sure what was the motivation for that change. Yes. Yes, I'm not totally sure, sorry.
No worries.
The cut was not always in FAR. When has been used a cut in SNR?
So for all three analyses in the past, they combined a cut in the FAR, in the false alarm rate, and in the signal to noise ratio.
Or the end?
An end, I think.
So,
it was
so more restricted than just
yes, it was
either
more
of the
restrictive. Yeah, this was less restrictive.
Okay.
Yeah, it's a good point, but I will have to check on that. Okay, so for the analysis in this case, I am showing here the priors used for the other two population models that were considered together with the power law plus Gaussian peak. So for the power law plus Gaussian peak, the priors are basically the same ones that I showed previously in the other case here. So that's why I'm not showing it again. But for the multi-peak and the full pop, these are the priors used for all the parameters of the different distribution models. So as you can see, the full pop model has like a considerable number of parameters compared to the other two population models, but that's also because you are spanning the whole range of the CVC population and accounting for things such as the mass gap and those things. And also here you have the possibility to get two peaks, while in the power law peak model you only have one peak in the distribution. Here in the multi-peak you also have two peaks. That's also why this has another like 3 or 4 more parameters for this mass distribution, but in any case. So these are the constraints on the mass and merger rate evolution models using this catalog information, both gravitational wave and galaxy catalog information together. So the solid curves represent the median of the distributions that were obtained, and the shaded regions represents the 90% confidence region of the distributions. So as you can see, for the power law peak and the multi-peak population, you start from around 5 solar masses, more or less, because this is used only for binary black holes or a system which has the primary as a black hole. But for the full pop, you start from around 1 solar masses. So that's because you are also including neutrons systems with a neutron star in the system. So with the multi-peak and full pop models, there are 2 peaks around these values. The difference between the two quoted results here are because this is around 68% confidence level, and this is 98% confidence level. If I'm not wrong, it's around that confidence. The peaks are located at these 8 solar masses and 26 solar masses. But when you use the power law plus peak model, you can only identify 1 peak because that's how the model is built, basically. So you cannot do more than that. So in that case, you get a peak which is close to this second peak in the other distributions. So that's basically the idea here. So 1 peak is around here for the multi-peak and the full pop, and the secondary and the other peak is here, which is also captured by the power law plus peak model. Here it is plotted the merger rate evolution that is obtained for the assuming different mass models. So basically these analyses were run or were performed using different mass models, and these give you different constraints on the merger rate evolution. So for the power law plus peak, you have this magenta color. For the multi-peak, you have the yellow color, and for the full pop, you have the blue curve here. Okay. Now, how the mass modeling impacts the estimation of the Hubble constant? This is a very important question. So here is that's shown for the dark siren analysis. So here for dark siren analysis is meant the analysis with galaxy catalog information included, but also constraining the population parameters together with Hubble constant. And this plot is the result of the marginalization of the Hubble constant over the other population parameters. So for the power law peak model, we have this magenta curve here. For the multi-peak, we have the yellow one here. And for the full pop, we have this blue curve here. And the prior on H0, as I was telling you before, is a uniform prior between, in this case, 10 to 200 kilometers per second per megaparsec. Yes.
Of this plot is there a huge degeneracy between H0 and astrophysical parameters?
Yes, yes, of course. And we can see that the full pop, which allows you to capture more details about the CVC population, like more peaks, but also it allows you to explore the neutron star mass range, allows you to have these different constraints. I mean, it allows you to extract more information from the mass spectrum, and this information is crucial to constrain the Hubble constant. So that's why there is like this difference. But one thing that's mentioned in the paper is that even though there is this difference, within the confidence intervals of these different estimations, the estimation of the Hubble constant is in agreement between the different estimations. So, yes.
So then after this plot, I have a really basic question then. So it seems that the mass distribution that had more parameters seems to fit better the data and give you better constraints, right?
Okay. That's
why not to extend it to more and more and more and improve the constraints up to?
Yeah, that's a difficult thing to claim rigorously, because first of all, they compare the base factor between only the power law peak and multi-peak population, because there is also one thing that I forgot to mention here, and the difference in the number of events. So for the full pop here, you can consider more events in the analysis, because here you can consider also the other 5 events that has a neutron star in the system, at least one. But for the multi-peak and power law peak here, you only take the 137 binary black holes. So that's another difference that I forgot to mention that is also important. So it's difficult to compare this also because of that, also because the mass models don't span the same mass ranges for all the cases, so it's not easy to compare them.
So you didn't try to, for example, validate each of them with the same number of events in the same redshift range to assess whether this is a difference coming from the modeling, or it's coming from the population, or it's coming from the...
Yeah, that was not done. Like considering, for example, full pop only with binary black holes and compare with this, no, that was not part of the paper, as far as I understand, yes. As far as I remember, yes.
No, thank you.
Was not, yeah. And yeah, so they don't completely make this comparison. Like, yeah, it was until this plot. Like, this is the most you can get from the paper. Okay, and now since the the multi-population model, the full pop model is very interesting because it spans the whole CVC range of masses. This plot is shown, which is showing the constraint, this reduced corner plot showing the constraints on H0, the location of the 2 peaks, and the maximum mass of the distribution. So these parameters are constrained this way. These are the 2D contour plots. The solid contours are representing the 68.3 confidence region, and the And this other one is the 90% confidence region for the 2D distributions. This is using the full pop mass model and also taking the Galaxy Glade Plus catalog information in the analysis. Okay, now this is one of the main plots, this is one of the main results presented in this paper, and this is the estimation of the Hubble constant. This is the marginalized posterior for this parameter for these different cases. So the yellow one is the bright siren, and as I mentioned many times here, there is only one bright siren so far, which is GW170817. This is the posterior that you can get with that event. Then there is the posterior that you can get on H0 using only mass model information, which is the spectral siren. In this case, this is for all these three scenarios, the spectral, dark siren, and dark plus bright sirens. This is assuming the full pop mass model that I have been mentioning so far. And so the orange curve is for the spectral siren case. The blue is for the dark siren only case. So you are not including the information from the from GW170817. And then the black curve is the combination of dark siren and the bright siren. So in this case, you have all the information coming together for the estimation of the Hubble constant here. And this is the value you get, the estimated value you get for the black curve. So 76.6 plus 13 minus 9.5 for the 68% confidence, and this one is for the 90%, 98%, or 98%. I forgot exactly the percentage, but it's around 90%. So this is one of the main results. And here, this table summarizes the different estimations that have been published so far for in different articles. So, for example, we have the bright siren estimation here. We have the estimation with the bright siren on 01 and 02 events. This was published by LBK. This was also published by LBK. This is with 01, 02, 03 events, and this is with 01, 02, 03 events, but this has more events. And the difference in the colors are that this blue is the dark plus bright siren analysis, and this is the spectral plus bright siren. So probably in this case, for the dark plus bright siren, the dark one was with a fixed population model. And in the spectral case, they didn't use the catalog information. Then there are these two results that I mentioned before that were published when ICARO GW and GW Cosmo were upgraded to do joint constraints of astrophysical parameters of the population models, incorporating galaxy catalog information here. So this is the result that was published by the ICARO GW team, and this is the one that was published by the GW Cosmo team. So you can see that they consider different number of events. And then there are these two constraints, one for the spectral siren case, using the whole population of CVCs with the full pop mass model. And this incorporates not only the mass model information, but also the galaxy catalog information. Also, both of them incorporates the bright siren event in this estimation. And you can also see here the two curves for Planck and Schuss values. So both of the results are in agreement with the estimated value of the Hubble constant with gravitational waves so far. They are both within the confidence level regions, 68 and 90% in all the cases. So yeah, this is what we have so far for this. Okay, and I wanted to talk about also the MDC work in which I was involved, but I think I am left of time now, so.
So I have two questions and one comment quickly. So in these results you're showing, I didn't understand why you go from like using 40-something CBCs to 140 CBCs and the error bars don't improve. Do you know why? From the, from these results compared to the last ones?
Okay, that could be due to several reasons. I'm talking from my point of view, of course, here. And one of them is probably that the O4A events were not very well localized, so the catalog information was not helping that much. You also have different population models, so it's hard to compare the different results here. And I would say those are the two things to have in mind. But if you compare with this one, well, this has 7. Yeah, it's just very few events. But I would say those are the two main reasons why this could happen. But I will have to check what are exactly the comments on that.
Okay, thanks. And in the previous slide, if you can go back. So, like, one comment I have is that looking at the blue curve as compared to the orange curve, it doesn't seem the Galaxy catalog is helping. And it seems that the mass spectrum is doing everything. I don't know if you agree with that. And the question about this is also whether you did the dark siren, but using the different mass models, to see whether these big changes that you have because of the mass model, they get more robust once you have the Galaxy catalog?
Sorry, the last thing?
So if you did the dark side analysis, but also with different mass models inside, to see whether the result gets more robust once we have the Galaxy catalog, more robust against the different mass models, I mean.
So this is the dark side analysis incorporating
this is the dark side. Sorry, I thought this was just the spectral sirens.
No, this is with the catalog as well.
Okay.
So answering the first question here regarding the difference between spectral and dark sirens, I would say yes, the spectral siren, the mass model distribution is helping a lot to get these constraints. The catalog also helps to improve a little bit the result, but okay, this is within some uncertainty levels or confidence levels, so they are pretty similar, but that's because of different things that we need to take into account, like the sky localization of the events. If the sky localization is not very good, then the Galaxy catalog information will not help very much. Also, the catalog that you're using here, so in the K-band, this Clade Plus catalog is not very complete, so it's not there could be other catalogs in the future that could give us better constraints because they are more complete in other bands, like using other bands could help, for example. And also the thing is here that for many of these galaxies, the redshift information is coming from photometric redshifts instead of spectroscopic ones. So the errors in the redshift also, if the redshift is not very well estimated, so the information that you get is not gonna be so useful compared to when you get better estimations of the redshift, for example, using a spectroscopic measurements, but that's more difficult because to get this spectroscopic redshift is expensive, it's costly, and especially for gravitational wave cosmology, you need this kind of information coming from all the sky, because gravitational waves are coming from all the sky, so that makes it more difficult as well. So all those things you need to take them and considering them and have them in mind when looking at these results.
Thanks.
Thank you.
So first of all, thanks for
Thank you.
the lecture. So my question is, like, the mass model is very important, as you show with the graphs. Like, it changes a lot of the behavior of your distribution for P of H0. So my question is, if there's a way, like, to be model agnostic or try to predict that function instead of using a model with some parameters, maybe using inference, or I don't know.
Okay, yeah. In principle, yes, you can try to use some non-parametric or some kind of model agnostic mass distributions. These are parametric ones, but then you will also have a lot of parameters, and then overfitting can come around. Yes, so that could happen. But yeah, that's important. But and regarding the prediction of the distribution, I think that's something that right now is not so feasible. I mean, we would need to understand very well what are the processes behind these binary black holes and binary systems in general, how they are produced in the universe, how they came to merge, and all these things. And I think right now people are investigating it, but it's not very well understood, as far as I understand it.
Okay, let's take Sergio again.
Thank you very much.
But you said you have something more to say, right?
Yeah.
Let's do the following. So people with urgent business, just leave, don't worry. And I will stay. Whoever wants to stay, we go on.
Okay, thank you. So I will just talk about very quickly about this blinded MDC challenge that we were involved in. And this work was published a few months before the OFRA results. So the idea was to check on the statistical and systematic effects that may arise when you are doing this cosmological analysis with gravitational wave data. So for this blinded mock data analysis, the idea was to create some simulated gravitational wave events. This was done by a simulation team. And then there is an analysis team that is in charge of analyzing this data. But the analysis team does not know that the analysis team don't know what are the parameters of the population, of the mass model and merger rate model, and not even the Hubble constant value that was used to create the mock samples. So, and these parameters of the distribution, the Hubble constant, and the merger rate evolution, they were chosen in a random way. So that make it more robust in the sense that the analysis not only not know very well what are the parameters chosen, but the simulation team does not choose some specific values, but they are chosen from some distributions, and then they are randomly selected. So that's mainly the idea here. And there were two scenarios that were considered. One, just to study statistical effects in the analysis. So this is the vanilla case scenario, in which you consider the same population model for the generation of the mock data and for the analysis. So that's the vanilla case. And in the vanilla case, we assume that the 4 observing runs with some specific data cycles for the different detectors. And then there is the second scenario that is used to study or address systematic effects. In this case, the systematic effects arising due to a mismatch between the true distribution used to generate the mock data and the distribution used for the analysis. So that was the idea. And in both cases, the merger rate evolution was modeled with the Maddow-like Dickinson distribution. Okay, so for the redshift-dependent case scenario, I forgot to mention, the primary mass is a power law plus peak Gaussian, the PLP, the PLG model, or PLP, And in the redshift-dependent case, it's like the same distribution, a power law plus peak, but in that case, the parameters of the distribution, like the power of the power law and the mean of the Gaussian, the width, all of those parameters have a linear dependence on the redshift. So that's why this is redshift dependent. So here you can see the different, how the distribution of the primary mass changes as the redshift is changing. So the blue one is for redshift equal to 0, and this magenta is for redshift equal to 1.2. So you can see there is some different behavior at different redshifts for the mass distribution. So for the vanilla scenario, there were some 286 detected events applying a SNR, a signal-to-noise ratio criteria, above 10. So basically, whenever an event has an SNR above 10, we deem that event as detected. So out of all the events that were produced in the MOG data generation, these were the ones that were detected. So these detected events have this distribution for the luminosity distance, this one for the primary mass, and this one for the secondary mass. So for the primary and the secondary, you can see that the distribution more or less follow the assumed distribution when creating the mock events. And then we have the redshift-dependent scenario with 80 detected events with an SNR above 12. This is the distribution again in luminosity distance, this is in the primary mass, and this in the secondary mass. And now here, this is a bit more messy than in the other case because of this redshift evolution. Then, these are the priors that were used for the analysis, both for the vanilla and for the redshift-dependent case. The priors were a bit different, especially in the Hubble constant, because the analysis didn't know this, but...
Sorry, about the absolute number of detection, it was fixed by given observation time, or how was fixed the number of detections?
Oh, okay, so you have this observing time, 3 years for the vanilla case and 1 year for the redshift-dependent case. Okay. So the redshift-dependent case is only without for sensitivity.
And those are the duty cycle, 0.6?
Okay. Exactly. Those are the duty cycles of each round of observation. So for the vanilla case, we consider the 4 observing runs, but for the redshift-dependent case, only 4. Okay. And then the criteria was the SNR threshold in this case. So depending on the SNR, the events were deemed as detected or not. Then for the analysis, these were the priors. As I mentioned before, in both of the cases, the mass model was, for the analysis, was the same, was the power law plus peak model. But the only thing here different from one to the other is the prior on H dot, because in this case, as I was saying, the analysis team didn't know the value of H naught, but it turned out to be greater than this value, if I'm not wrong, or close to this value. So this, using this prior, the results were not very good, so the analysis were done again with a larger prior, and in that case, the results were a little bit better. So these are the estimation of the merger rate and the primary mass distribution for the vanilla case. These curves in orange represent the 68% reconstruction of these distributions coming out from the posterior samples. So as you can see in the vanilla case, we can recover both the merger rate evolution that is assumed to create the mock data and also the primary mass distribution that is assumed to create the mock data in both cases within the 68% confidence intervals. And this is the corner plot showing some particular parameters, basically the parameters that most correlate with H naught, which are the location of the Gaussian peak and the width of the peak. So in all the cases, the parameters are within the confidence intervals regions of the estimated values. So this is outside the 68% interval, but it's within the 99% confidence interval in this case, 98%. No, in this case it was 90% confidence, sorry, 90%. And these these solid lines represents the injected values. So that's why I'm saying that we can recover them in the vanilla setup. So basically, if the distribution of compact binaries in the universe, we are modeling it correctly, we can be confident that our estimation on H naught is robust. That's the main point here of this result that I will highlight. There were some statistical tests done on this event. So, for example, the number of injections. So, these injections is the number of simulated events that are used to compute the probability of detection. So, this is to compute the selection effects that I was mentioning for the likelihood. So, when you have around 10 to the 5, 10 to the 6 injections, your result is starting to become consistent. So, starting from 10 to the 5 injections, you have a result which works fine. And then this is an analysis showing what is the impact of different random realizations of the injection set. So 10 to the 5 injections, different sets randomly selected, and we were getting the same constraints on H naught basically in all these cases. Then other statistical analysis that were done was, for example, changing or varying the number of detected events. So starting from 150 and going up to 286, we can see that the estimation of the Hubble constant is pretty much similar for all these cases. Of course, when you are with the most number of events, you get the better, the constraints peak closer to the injected value. But the confidence regions probably are very similar. So the estimated value is within the confidence interval, but for a larger number of events, the peak is getting closer to the injected value. And then this is another test checking on different random realizations of gravitational wave events. I think these were around 50 events each, or 100, but it was some specific number, which I forgot now, sorry. But the main point here is that if you use the same number of events, your results are pretty much the same within the confidence interval regions. Then for the redshift-dependent case scenario, we have these results. So as you can see, this is the injected value here for the Hubble constant, it's more than 100. And even if there is some redshift evolution in this case, you can still see that the constraints on the cosmological parameters, especially H naught, is still within the confidence regions of the parameter space here. So that's another of the main points here. And for these mu g and sigma g parameters, here the constraints are just a number because the analysis was assuming a fixed population model. But remember that the injected value in this case is not a fixed value, but a value that changes with redshift linearly. So this is how the value of this peak, the location of the peak and the width changes with redshift for the two parameters. And this is the posterior, the marginalized posterior for each of these parameters. So as you can see, all the values that are within the redshift range that was shown here, are within the confidence, 68 confidence region probably, or the 90 at least, confidence interval region of the estimated value of each of the parameters. Okay.
Location of the peak and width?
Yeah, this is the location of the peak and this is the width.
For the single peak model?
For the Paolo single peak, yes. For the Gaussian peak, yes. Okay, and now this plot shows the marginalized posterior somehow of all the population and cosmological parameters here. This omega mater parameter was also sampled, and also the merger rate evolution parameter in this case was sampled here. So as you can see, for most of the parameters in the vanilla case, they are within the 90% confidence regions. For all the parameters of the shows that if you assume the same population model for the analysis than the one used for creating the data, you have robust results. And for the redshift-dependent case, we can see that most of the parameters are also within the 90% confidence region. There is only one parameter going out from confidence region here. But in general, this shows that even if you have a mismatch between the population model and the true model, you can recover the parameters kind of well, right? So the value of these parameters in the redshift-dependent model is the value of the parameters at redshift equal to 0. So that's one thing I should mention here. Okay, and now just to finish, some summary of what I've presented today. So there are novel methods for population and cosmological joint inference using gravitational wave data that incorporates EM counterparts information and galaxy catalogs information as well. These methods have been applied to O3, GWTC3, and GWTC4 catalogs data to constrain the Hubble constant. And we hope that future gravitational wave data would shed light on the Hubble tension, maybe with a future network of detectors. This would be better. The blinded MDC analysis for the vanilla scenario shows that if you assume the true population distribution for the analysis, in this case for a mock data case, but this can be extrapolated to the real scenario, you can recover, you can infer your model parameters and also the cosmological parameters without bias. And the other key thing is if there are some departures from the mass model, in this case which are redshift dependent, then there would be some impact on the inference of the astrophysical population parameters, but this will be not very pronounced, and it will be a bit more pronounced on the inference of H0. But one thing that I would like to highlight here is that from the population paper of LBK with the GWTC4 catalog data, there is no claimed evidence of redshift evolution in the mass distribution. So these things are not so relevant right now with the current data. Thank you.
Okay. You have not exhausted all the questions.
Sorry for asking more questions. So, is there like a number of events that you need to see, like detect with these gravitational waves to reach a precision that will help, like, to reduce the tension or explain the tension?
Okay, good question. I'm not sure exactly if there is an estimation of that, of the number, but you also need to consider that not only matters the number of detections, but also the precision. Yes, like how well you can estimate in the individual event parameters, the sky localization. So if you have more detectors, it also, and well located across the Earth, it also helps to get better constraints. Also, if you are considering, for example, the dark siren analysis, how well is your catalog, galaxy catalog data, and also the other key thing is we are expecting nature to give us more bright sirens, because bright sirens would allow us to get better constraints, because that's a more direct way to do it. And in that case, I think there are some estimations, going back, I think there are some estimations on the number. For example, for bright sirens, I've seen some papers, but I don't remember now the authors, but there are some papers that quantify this, that forecast how well you can constrain the Hubble constant as you increase the number of bright sirens, for example. I don't know if there is something similar for dark sirens right now, but probably there is something. And I think bright sirens would be very great if we detect more, but so far we haven't.
Yeah, I mean, like detecting a bright siren is way more complicated, right? Because the objects have very lower masses.
Yeah, that's one thing. Yeah, when usually we expect bright sirens coming from system with a neutron star, so this is a lower mass system, and this makes the gravitational wave signal smaller so it's difficult to detect it in that case. So it would have to be closer to us. And also, when you detect these kind of systems, the other problem is that you need to be confident of the electromagnetic association. So there are some cases in which there have been some candidates, but the electromagnetic association is not very good, so we stop there.
Okay, thanks.
Thank you.
Okay, I think now we can really start.
Thank you. Thank you very much.
We already thanked you 3 times. That's enough.